Today, we are diving into a really cool puzzle that sits right at the heart of computational fluid dynamics. You can think of it like a detective story, all about how simulations figure out one of the most basic forces in nature, pressure. So, let's get right into it.
So here it is, the central mystery. In a fluid simulation, if you don't have a direct equation telling pressure what to do, how does the fluid even know where to go? I mean, how does it know where to push? This is the exact question that baffled early programmers, and we're going to solve it together.
Okay, so our story begins, just like any good mystery, with a set of rules and a critical piece of missing information. This is what we call the enigma of pressure. These right here are basically the laws of physics for our simulation, the famous Navier-Stokes equations. You've got the momentum equation, which tells us how forces, like pressure differences from one spot to another, change the fluid's velocity. And then there's the continuity equation, which is even simpler. It just says you can't create or destroy mass. Simple, right? What goes in must come out.
But if you look closely, you'll see something strange. We have all these equations that are all about velocity. They live and breathe velocity. But there's this ghost in the machine. That pressure term is sitting right there in the momentum equation, pushing the fluid around, but there's no other equation that tells us how to actually calculate the pressure itself. So, where is it?
And here is the absolute crucial clue. For incompressible flows, like water, the density is constant. Now, for compressible flows, like air, you can use something called an equation of state to link pressure and density. But here, with water, that link is totally broken. Pressure kind of becomes this implicit variable. It only exists to make sure the velocity field is obeying the law of mass conservation. And that's exactly why there's no simple, separate equation for it.
So, how in the world do we find this sneaky, elusive pressure? Well, the first, most logical approach seems simple enough. But, as it turns out, it leads us straight into a trap.
The most intuitive way to go about it is called a collocated grid. You just divide your simulation space into a grid of cells, and you store all your variables, pressure, x velocity, y velocity, at the exact same points, usually right in the center of each cell. It's clean, it's simple. I mean, it makes perfect sense. What could possibly go wrong?
Well, it turns out this super neat and tidy method falls right into a trap called the checkerboard paradox. And this is a classic red herring in our little detective story that sends the entire simulation completely off the rails.
Just imagine a pressure field that jumps wildly from high to low between grid points, just like a chessboard. To us, looking at it, it's obviously a very bumpy, chaotic field. But for the simulation, using that collocated grid, when it tries to calculate the pressure difference by looking at its neighbors, the high pressure point on one side gets perfectly canceled out by the high pressure point on the other. The simulation is literally blind to these oscillations. It sees a completely flat, uniform pressure. And with no pressure difference, there's no force. And the results, well, they're just non-physical garbage.
Okay, so the collocated grid was a total dead end. To solve this mystery, we're going to need a breakthrough, a completely different way of looking at the problem. And this is where the hero of our story comes in, the staggered grid.
This image just illustrates the core idea so brilliantly. The key, which was developed by pioneers like Harlow and Welch, was elegantly simple. Just stop putting everything in the same place. This was the eureka moment that cracked the whole case wide open.
So here's how it works. You keep the pressure values right there at the center of the grid cells. But, and this is the genius part, you move the velocity components, so they're calculated on the faces of the cells, staggered in between the pressure points. So the x velocities are on the vertical faces, and the y velocities are on the horizontal faces. Now, what's really fascinating here is you can see why this works so well. On that old collocated grid, the checkerboard pressure was invisible, remember? But on the staggered grid, the pressure gradient that drives the velocity is now naturally calculated between two adjacent pressure nodes. It can't be fooled. It immediately sees the pressure difference, it correctly calculates a strong force, and it smooths out those non-physical jumps, forcing a realistic solution. It's just elegant.
So we have our staggered grid. It's the perfect tool for the job. But how do we actually use it to solve for both pressure and velocity at the same time? Well, this clever grid is the foundation for one of the most famous algorithms in CFD history.
It's called the simple algorithm, and it was developed by Petonker and Spalding. And really, at its core, it's a guess and correct procedure. It uses that awesome staggered grid to iteratively chip away at the problem, getting closer and closer to the right answer with every single cycle.
Here's how the loop works. First, you just guess a pressure field. Seriously, any guess will do to get started.
Second, you use that guessed pressure to solve the momentum equations and get a temporary velocity field. But, and this is key, this velocity is almost certainly wrong. It's not going to conserve mass. That brings us to the most brilliant part in step 3. You use the continuity equation to create a special pressure correction equation. Its whole job is to figure out exactly how much the pressure in each cell needs to change to nudge the velocities just enough so that mass is conserved. Then in step 4, you apply those corrections to update both your pressure and your velocity fields. And finally, you just repeat the whole thing over and over until the corrections get super tiny and the solution finally converges to physical reality.
And that's really the beauty of it. The main goal of this whole correction process is just to nudge that velocity field around until it perfectly satisfies the law of mass conservation. It's an incredibly powerful and robust approach.
So the takeaway here is this. We started with a huge mystery, no equation for pressure. The solution was to cleverly repurpose the one equation that doesn't even have pressure in it, the continuity equation, and turn it into the very tool we use to find the pressure. It's like a brilliant piece of mathematical jujitsu.
And that really is the key. You know, sometimes solving a really tough problem isn't about looking harder at the same old variables. It's about stepping back, looking at it from a completely different angle, and realizing the solution was hiding in plain sight the whole time, just not where you expected to find it.